Let's look at a really important and useful idea of the Fourier transform, and that's the idea of symmetry. So we've seen some of this before, but it's well worthwhile just going over it again. We've seen previously, we mentioned the idea of an even and an odd function. So I have an even function here, which is a square function, and it's symmetrical around the y-axis, so we can flip it on the y-axis and it will land on top of itself. So that's an even function. Mathematically, we could say the value of a function f at t, so there's a point t there, f of t is that point there, so it's that height, is the same as the value of f at minus t, so go to minus t, and I still go up to the same height. Okay, so that's an even function. Now an odd function here, it's similar there with a square wave, but on the negative side, negative axis, it's flipped over on this t-axis. So you can see here that if we call this function g of t, then the value of g at t there at this point t is this height here. But if I go to g of minus t, so I go to the minus t section, the value now is not the positive height t, but the minus height t. So we could say that g of t equals minus g of minus t, or equal to, we could have said that g of minus t equals minus g of t. So that's our even and odd functions. So let's go and build up a particular function using even and odd terms. So most functions out there won't be purely even or odd, but will be a mixture of even and odd terms. So in order to split a function into its even and odd terms, the even terms given by the f of t plus f of minus t upon 2, and the odd terms given by f of t minus f of minus t upon 2. So here's an example, and this is the example we looked at when we did the Fourier transform. So this is a square function of height 1 and length 4. So if we looked at f of t, so f of t upon 2 would be a function at its height of a half and length of 4, and f of minus t upon 2 would be a function which would be height of a half, and it would be mirrored here on the across the y-axis. Okay, so we have this here. So when we add both of those together, we're going to get this function here. Now we'll do the same thing here for the odd part. So the odd part is going to be f of t upon 2, which is the same as this one here. And then we're going to have minus f of minus t, which is this term here. When we add them together, we get this little function here. Now when we add both of these up, you can see that when I add this section here to that section there, we get a value of 0. When I add that section there to that section there, we'll get our height of 1 and our length of 4, which is our original function. So let's look at multiplying two functions together. If we multiply an even with an even, we get an even function. So here's a little proof here. Let's say we've got a function f of t which is even, and a function g of t that's even. Then we can write the function f of t as f of minus t, and g of t as g of minus t. So if we multiply both these together, we'll get a third function, we'll call that h of t. So therefore we can say that h of t is going to equal h of minus t, which is these two multiplied together. So you can see then that this term here, this h of t, is an even function. So even times even will give us an even. If we multiply an odd function with an odd function, we'll get an even function. So let's say f of t is odd and g of t is odd. Then we can write f of t as minus f of minus t, and the g of t can be written as minus g of minus t. When we multiply this right hand side together, the two minuses are going to cancel, and you're going to end up with the f of minus t times g of minus t, which will be a third function which we'll call h of minus t. So we say that h of t equals h of minus t, which is an even function. So we can say that odd times odd equals an even. Now the last one here, odd times even equals odd. Well, equivalently we could say even times odd equals odd as well, so only to do one of them. So let's say we have our function here, and let's say the g of t is the odd function, and the f of t is the even function. Then we can say that f of t can be written as f of minus t, and the g of t can be written as minus g of minus t. So when we multiply these two together, we're going to get a function which is a minus h of minus t. So this is an odd function, h of t. So odd times even will equal odd. So now I've seen this before a couple of times, but we'll just add it in because it belongs here within this video. We've seen that if we were to draw out an odd function, so for example this sine function, if we were to integrate this odd function from minus infinity to infinity, we would get an answer of 0, because this area would cancel with that area, this area here would cancel with that area, and so on and so forth, so there would be no value. If we were to take an even function, say for example the cosine function here, then we could say that this area here will cancel with this one, this area will cancel with this one, but the area here will be an actual value, so that won't cancel with that because both of them are above the line. So therefore we can say the integral from minus infinity to infinity of an even function does not equal 0. So let's look at the even and odd symmetry mathematically. Then at the end we'll draw a nice little kind of diagram that will explain it all visually. If we take a function f of I omega, then we can write the Fourier transform as a separated function of an even function and odd function. So we take a function of time and we split it into an even part and an odd part, and we'll take the Fourier transform of both of those. So we'll have the integral from minus infinity to infinity of the even part of the function times e to the minus I omega t by dt, plus the integral from minus infinity to infinity of the odd part of the function times e to the minus I omega t by dt. We can now go in here and we can replace the e to the minus I omega t with a cos omega t and a minus I sin omega t. And we can do the same with this side here, replace the e to the minus I omega t with a cos omega t minus I sin omega t. So therefore we'll have 4 terms here, this 1, 2, 3 and 4. But 2 of the terms are going to disappear because of the symmetry and the evenness of these functions. And we can say that in this instance here, the even part here times the odd part here will give an odd part, and we'll be integrating an odd part from minus infinity to infinity, which will give us a value of 0. So this term here will disappear, and you'll only be left with the first term here. Similarly, if we look at this side here, if we were to multiply this odd part of the function with this even function, we would have odd times an even, which would equal an odd function, and we'd be integrating that from minus infinity to infinity of an odd function, which will give us a value of 0. So this term here will disappear, and we'll only be left with this term here. So from these 4 terms we'll only get 2 terms. So these are the 2 terms here. The Fourier transform of an function I omega will equal the integral from minus infinity to infinity of even part of t cos omega t by dt minus I times the integral from minus infinity to infinity of the odd part of t times sin omega t. Now we've used this symmetry throughout several of our videos whenever we were working out, say for example, the Fourier series of even and odd functions, and we used this in order to simplify the mathematics. So we have seen this before, so there's nothing new in this. So let's look at a function f of I omega, and we'll split it into the 4 components. So we're going to have a real even component of I omega, we're going to have an imaginary even component of I omega, we're going to have a real odd component of I omega, and an imaginary odd component of I omega. So if we were to take the Fourier transform of each of these 4, then we can say that the first one here is going to be the integral from minus infinity to infinity of the real even part of t times cos omega t. The second term here is going to give us our imaginary even part of cos omega t. The real odd part, well, it's going to give us our imaginary odd part of t times sin omega t, and the imaginary odd part is going to give us the minus I times the real odd part of the function f of t times sin omega t. Now I suggest you sit down and have a wee think about that and convince yourself that these four do actually occur and they do map into each of these. Now what we want to do is we want to equate all of these terms with the terms for the Fourier transform. So we'll do that in the next slide. So what we end up with is the real even part of an even function I omega will give you a real and even function of time times cos omega t. The imaginary even will give you an imaginary even part of a function. The real odd will give you an imaginary odd, and the imaginary odd will give you minus the real odd. So let's look at this, and it'll be more apparent whenever we see it in a diagram. And I wouldn't tend to remember this. Once you've seen it once and you've seen it derived once and you understand it, you know where it is and you can go back and get it if you ever need it. But it's not something that I tend to always keep in my head. I have a nice little diagram here, and this is the kind of thing that I would tend to remember. So these are the four symmetries all drawn out in a nice little diagram, and this is the kind of thing that would be useful to remember. Now, it turns out we're only really interested in symmetry number 1 and 3, because symmetry number 2 and 4, well, these have got imaginary parts of time. So in this case here we've got an imaginary time axis. In this case here we've got an imaginary time axis. Now, we're not dealing with imaginary functions of time, we're dealing with purely real functions of time. So we're only really interested in 1 and 3, but we'll talk about all four of them anyway. So let's do 1 and 3 initially. So if we had a real even function of time, so that's a little square function there, and that's real, purely real, and it's an even function. It would map through the cos omega t surface, and it would give us a real even function of frequency. And you can see that sinc function there is an even function of frequency, and it's a purely real term. There's no imaginary terms there, there's no imaginary axis. So the real even part of time will give us a real even part in frequency. Now if we were to look at a real odd function of time, so here's an odd function here again, which is a little square function which we've seen previously. Now that maps through the sine omega t surface, but there's actually a negative sign in here because we've worked out that the real odd part of time in frequency will give an imaginary odd part of frequency, and it would be negated. So we've got that drawn out here. In the frequency domain we've got this function here, which is a purely imaginary function that lies on this axis, and you can see that it's an odd function as well. So those are the only two we're really interested in, but we'll talk through the other two. So the question at part number 2, if we had an imaginary even function of time, so it's purely imaginary, it's this axis here, then it's going to give us an imaginary even function in frequency. So here's an imaginary even function it gives us in frequency, so it's in this axis here, and you can see it's even. Also an imaginary odd function of time, so here's an odd function of time, it's in the imaginary axis. It gives us a real odd function of time, so this is a function that lies in the real axis, and it's an odd function. So those are the four symmetries, and the only two we're interested in is numbers 1 and number 3. So that's all I have to say about symmetry. Symmetry is a useful part of the Fourier and Laplace transforms, and it's a useful thing to understand, and we'll be able to apply it in order to simplify an awful lot of the mathematics that we do. So thank you for listening, and goodbye.